Thank you everyone for joining today's ELISA seminar talk. We're very delighted to have Lukas to give us the talk on certifying Linux, state of the art, and his reflections after 8 years of doing the work. Lukas, I think many of you already know him. He's a safety software key expert currently at Elektrobit. Lukas is also a technical steering committee of the ELISA project, currently also a governing board member. And Lukas has been involved in the ELISA project since its inception. So we really appreciate Lukas's involvement and contribution, and delighted to invite him back for this talk. So I'm gonna pass the baton to you, Lukas.
Yeah, thanks, Min, and thanks for the introduction. We're going to talk about certifying Linux and say my experience and things I've observed in the last 8 years, looking into this aspect of certifying Linux. So let's get started. So what's the purpose of this presentation? I want to give you an overview of the thoughts, ideas, and approaches that we have come along to make use of Linux in safety critical systems. And we're going to put these approaches into different classes, point out the difficulties and challenges for approaches of those classes. And again, right, I cannot talk about, let's say, all the, private things that I have seen from other various companies. So I'm really showing only a selection of publicly known work, as well as kind of abstractions of things that have been presented to me or that I have discussed with others. Also, if we talk about the difficulties and challenges, they really do not judge or discredit the value of a certain approach or its feasibility. It just tells you, okay, if you're trying that, that might be something that you need to tackle. But I think all approaches are somehow valuable or potentially feasible with some kind of work. Okay, so why are we talking about the past 8 years? So a bit of a history to it. In 2015, there was an industrial research project under the governance of SADL that went on for 3 years. And in 2018, we actually summarized this work. So Nicholas McGuire, Andreas Placek, and me summarized this work in a paper called Certifying Linux, Lessons Learned in 3 Years of SIL2LinuxMP. And as continuation, we're now in basically the 2024. And I've given this presentation in October 2023 at the EXIDA Symposium. And at that point, and currently we are actually already 8 years into this kind of investigation. So what's pointed out in this 2018 paper, we do address a few of those general misconceptions about how you would certify Linux. And we propose a number of measures from a layered system hazard analysis, similar to STPA, how to apply methods, or how to propose new methods into the normative framework of safety standards, how you can go into a controlled selection process, how you can analyze the development process with data mining and statistics, how to apply layers of protection analysis to Linux, and proposing a number of tools for maintenance and impact analysis. So if you want to know more about that, just have a look at that paper. It's publicly available. This project ended in 2018, and we continued this work in 2019 under the governance of the Linux Foundation. And that was the kind of introduction of the ELISA project. Again, if you're in this webinar, you probably know ELISA project. So we're exchanging on ideas, having activities, interesting activities among interested participants. The member companies provide the funding so that we can actually organize the exchange and meet. And what you will see in the different working groups is that there's a common understanding of Linux kernel functionality built up in the different domains. We're looking at different use cases. We're investigating measures and techniques. So STPA, the Raffia approach from CodeThink. Red Hat is proposing tools for requirements to test case mapping and architectural analysis. So you'll find much more on that on the different mailing lists and the blog post and so on. And when we're talking about Linux in a system, we of course have to explain a bit what is our system. I'm taking here the automotive context. So what you see is that in the vehicle architectures, we're moving towards more centralized computing units, so kind of zone computing, high performance computers for different zones like ADAS functions or IVA functions. And this is getting more and more centralized into kind of high performance systems. These high performance systems are usually ECUs with some kind of system on chip and watchdog that's connected to the Ethernet. And of course, if we look into how do we have a software architecture in these ECUs, there's a general conception that you have some kind of applications that implement the actual safety functions you're interested in. They're running on some kind of middleware. And then there's an operating system. And there, of course, C library and the Linux kernel are kind of the interesting choices that you could take when you want to build such a system. We're going to look into exactly this, say, Linux kernel in such an assumed system context. So when you build up your safety argumentation, you're going to eventually reach this point where you're going to say, okay, I have used Linux in my system, and my top level safety argument now is using the Linux kernel in this system is going to be acceptably safe due to, and then you have to come up with your argument. And we're going to look at 5 different classes that you can use to make that argument. You could either lower the criticality and fault propagation likelihood, you can use diversity, you can use proven in use, you can use, you can show that your product meets a certain quality, or you can show that the process during the development of that software meets a certain maturity. And we're going to look into these different approaches now, step by step. So the first one, to lower the criticality or fault propagation, the general idea is that we mitigate the propagation of faults that are emitted from the kernel by some kind of design, detection, and control of the system surrounding it. Typical examples are to use coded processing in the application software so that you can actually detect some kind of misbehavior by your surrounding platform. Another approach is to use somehow safety layers in the middleware so that you can actually detect certain inconsistencies from the APIs you use. That is also an approach that was used in the Thales SICAS project, I think now more than a decade ago. So the challenges with this approach is, of course, that the mitigation you are going to apply might be application specific. You really don't know if that's applicable for a general use case. Often you're making use of something in the application itself. The performance impact of coded processing and the safety layers is not to underestimate. Again, right, if you're encoding all your computing, you're going to lose a lot of performance. And again, you want to apply Linux in a high performance system, so performance does matter. And of course, what you're not getting away with is you still need to enumerate all the relevant faults that the kernel can emit in some kind of complete manner and show that the mitigations that you have, the detection and control, is actually sufficient and complete with regards to that enumeration. Otherwise, right, you have a fault propagation that wouldn't be accepted. Okay, so much to the first approach. The second approach, we are going to use diversity. The general idea here is that we propagate, or the kernel is going to propagate faults, and we know that we can mitigate them because the probability of them propagating into diverse systems is significantly low. Examples are that we use diverse applications and diverse user profiles of the kernel. So we know that when the application is using the kernel, it will be using it differently to different times with different functions, and hence the likelihood of functional misbehavior showing the same effects is going to be likely low. Another one is that you actually use different kernel implementations. So you could imagine using the Linux kernel and the BSD kernel. Both of them are providing a POSIX compliant implementation, but of course they are very different in implementation. They're created by different teams. They have a completely different code base from each other. They make different architectural choices and so on. You could also create diversity of the hardware architecture that you use. So there are, of course, multiple different hardware architectures that Linux supports. So you take two systems with different hardware architecture, and then you could argue that certain behaviors that are only visible in one architecture wouldn't be visible in the other architecture. You can apply a layer of protection analysis. And again, here we're showing that we're basically having multiple multiple gates, and both gates have to be passed so that a fault would be propagating, and then we show that the likelihood that both gates to actually fail to detect the fault is low, and by this kind of combination of protections we show sufficient coverage of faults and their likelihood. And a last approach would be to use the diversity of the kernel state and the probability of fault occurrence. Again, if you boot up a system that is as complex as the Linux kernel, you will notice that at its very lower levels, the actual kernel state is very different. So you actually don't have a deterministic memory layout, but you have a very diverse setup when you boot up two systems. And again, if you can show that this low-level state is actually contributing to the likelihood of fault failure propagation, then you can show that a diverse system would actually unlikely show the same fault propagation chains within the two diverse overall systems. Here's, of course, two challenges that I need to point out. First of all, there's actually very little guidance from the existing safety standards on what are the expectations on such a diversity argumentation. So you'll find a little bit information in the standards, but you have to dig a bit deeper into the literature to actually find out how to structure diversity argumentation and potentially what is considered good enough for such a system. And the second challenge is, of course, that coming forward with this approach to use diversity is going to put you in a difficult design decision with the overall system design, right? You might run over costs that people are expecting, or certain other requirements, such as performance or availability, also come into play when you look at diversity. Okay, so the first two we have done. The third one I'll mention for the reasons of completeness. Of course, you can move forward with a proven in use argumentation. Also, the general idea here is clear. We can actually collect data from existing deployed production Linux systems and then try to prove that these systems are sufficiently good for the use in safety critical systems. And the motivation is driven by the fact that the Linux kernel is most probably the one software that is running in the largest number of devices worldwide, right? We can kind of count the number of systems we would expect in the internet running Linux, the systems running Android, and the various systems and other, let's say, handheld customer devices. And you'll easily come up with a number that's probably close to the billion or even more. So it's clear that it is used very widely. But of course, if you look into the standards, so I'm looking into IEC 61508, part 7, Z2 10.1, and it boils down that proven in use requires you to show a number of aspects, and those are actually difficult to show for Linux. It requires you that the system has an unchanged specification. Well, it's pretty stable, but it's not that the specification never changes. So it doesn't really meet that, or only with specific flavor it meets that. You have to show that the systems run in different application contexts. I think that is actually a very nice point of Linux. We see that it runs in supercomputers as well as embedded devices, and has a wide range. We need to show that we have at least 1 year of service history. Again, you probably have seen that, but if we take updates into account, it's already getting more difficult to say, is it actually running for a year or is it never running for a year? So also here, that's difficult to argue. The operating time has to be according to the safety integrity level you want to reach, or the suitable number of demands. Here as well, if you want to reach, let's say, a mid-integrity level of SIL2 or SIL-B, we're talking about billions of operating hours. You can certainly show that, but already that's quite difficult or quite demanding for an organization to show that this operating time has been met. And I think now the last two are the ones that are most difficult, just due to the lack of information. We want to show that the operating experience we have is actually related to a known demand profile. Again, we know very little of how smartphones or how Linux is used in the internet. So we really don't know what's the demand profile these systems have that they're exposed to, as well as we don't know the demand profile of the safety function that we're considering. So getting a match on both of those is already quite difficult. And then, of course, we know that there are certain failures in those systems. And I think large Linux large systems companies that deploy large Linux systems in the field do observe kernel failures, but of course it's now difficult to actually do a root cause analysis on or an impact analysis on those failures. What would have gone wrong if this would have been a critical system? And of course, even more difficult, would have that led to a safety related violation and to an actual hazard in the system is really difficult to judge, given how long those fault propagation chains could really be. So also there, it's difficult, and I think it all boils down to one aspect, that we're talking about one software as the Linux kernel. The Linux kernel isn't really one software. There are thousands of public versions. There are non-public modifications done by the companies deploying those systems. There are different build configurations. You can modify boot and runtime. And you actually see multiple kernel updates per year, which you're just gonna deploy to your systems because they're either low impact bugs that are still of interest or security aspects that you want to address. And with that, you already are gonna move outside of that very typical proven in use consideration that the safety standards make. Nevertheless, you can use proven in use maybe by a different interpretation. So you want to collect data from existing deployed systems, but you need to show, okay, for which aspect are you using them? How are you going to generate evidence for specific functionality you're interested in, but not for the kernel as a whole. Okay, so let's move on to the fourth approach. And we are going to show that our Linux kernel meets a certain product quality. Again, we know the standards. They assume a certain development process, and they assume that specific work products and evidences are created. And of course, we could create those work products and evidence without actually considering the software construction process. So what we do have from the Linux kernel is we have a software requirement specification. Think of the POSIX standard plus the man pages. We do know that the implementation exists. So we have the code in front of us, and anyone can download that. And of course, we know that there are some tests, either some public tests or a set of internal tests that you have created that show that this code actually meets your expectations. Now, the challenge is, of course, that besides these three blue boxes of things that we really do have and are pretty clear, we have very little from the bits and pieces that are these intermediate work products. So a system of the size of a Linux kernel cannot be created without a design. So obviously, even if you look at the requirement specification and at the code, you must assume that it's impossible to create this code in some kind of way without going through a design process. We simply don't know anything about this design, right? We don't know the selected design. We don't know the alternative designs that were considered. And often it's because it's not formally tracked. It's either difficult to access or you don't know about it because you're not an active member of the development community, but considering it much more from a system integrator point of view. And sometimes it might be non-existent, but all of that is not to differentiate when you look at it. So we know, okay, there must be some kind of design, but we don't know anything about it. Also, unit tests, you'll find a few unit tests, but not the full coverage of your code. Again, there's something existing, possibly something missing. Similar for test results. These tests must be executed by others, but you cannot observe all the test results in a common database, for example. So all of these yellow boxes are not existent, and the traceability between those kind of difficult to access artifacts also does not exist. So now what can you do? We still have 3 starting points, right? So instead of trying to find out what is in this cloud, we're going to create some kind of other work products next to it to make this kind of cloud smaller or irrelevant. So of course, what we can do is we can take the software requirement specification and trace against the existing tests. Possibly we find out, okay, the existing tests aren't enough, and we create more additional tests. If we then consider, okay, this is actually commercially not feasible for the complete specification at hand, we can formulate constraints and say, well, we're not assuming certain APIs are going to be used, others are not going to be used. And with that, you argue at least some kind of relative completeness towards those constraints. You can, of course, run those tests, get test results, and with that, you've shown that your tests meet your implementation. Again, don't expect all tests to succeed. Probably some of them fail, but you'll find out, okay, there's some kind of misconception when you wrote the test, or some kind of different interpretation that's possible between the implementation and the requirement specification. Again, we're talking about mid-integrity, so that's not too surprising that there is some kind of interpretation gap in such descriptions. So also you don't have a design at hand. So what you can do is you could, of course, take the code and try to extract a design from that code. That design would then meet formal criteria that the safety standards ask for. And of course, you can use your local expertise that you might have to evaluate if that design is appropriate for your system. And again, you could look at the design and say, well, under certain constraints, it makes sense to use this code. And under these constraints, it's also reasonable to expect the system to do what you want it to do. Okay, so what are the challenges if you go towards this product quality argumentation? Well, first of all, right, we're doing this kind of reverse engineering, and we actually don't really know the actual architectural design decisions that the developers made, right? We're just extracting what we can see in the code. So what were really the choices on which were taken, we actually don't know about. Also, the extracted design can somehow claim unintentional properties because the extraction cannot really distinguish between something that coincidentally happened and something that was intentionally built into the system. Again, the extraction will just say, well, this happens to be the case, but you really don't know if it was by design or by coincidence. Your local expertise might not actually match the development expertise at the point where it was developed. So it could be that you actually don't understand the design as well as the developers that were initially creating it. So you might misjudge the suitability, or vice versa. You might have much more expertise at your table when you're looking at the extracted design, which the developers never had in mind. So you're putting some kind of expertise into that development that never existed. Also, it's clear that when you reverse engineer all of that, you actually have no feedback to the development itself, right? The code is largely untouched, and you don't really close some kind of feedback loop with the already existing implementation. And also the formal criteria you apply during this retrofitting was never applied during development. So the question is, would have that had positive impact? You really can't answer because you really don't show that. And after doing all of that, what you're doing here for this product quality argumentation, you'll find out, well, what you're going to deploy in the end is probably very close to that what you had at the starting point. So all of this retrofitting efforts might have been academically interesting or commercially expensive, but the software you're actually going to produce, or the software you're going to deploy, is actually still very similar to that what you had in the starting point. So alternatively to showing kind of a product quality, you could move forward of showing the process quality. So how does that differ? Well, we're not going to create these work products, but we're going to argue that they exist. And we're going to argue that they exist qualitatively, and then show kind of by afterthought that they must have been sufficiently well working and existent as the process, as the development process is actually sufficiently stable, meaning that we don't see surprising bugs or surprising obvious bugs, or some completely misconceived design. Again, we have the same starting point. We have requirement specification, we have implementation and tests. We acknowledge this unknown in between of intermediate results. And we're now going to say, well, we know that we cannot formally track them, but we know that they must exist. Otherwise, our development process would show very different behavior than what we can observe. Okay, so how do we argue that these work products must exist? We're going to look at the design. So the question would be, does the Linux kernel have a design? And we only want to show this qualitatively. So right, we can look in the internet and we'll find out there are university courses on Linux kernel design. Right? The professors could not come up with their slides and their tutorials on that if there would be no design existent. They are talking about something. There are books on Linux kernel design, so people have described how the system is generally working. We'll find mailing list discussions on the design alternatives if you do some kind of spot checks. And you can show, okay, there must be something in there. There is something there. So the question really remains is this thorough and effective, what we have now just found by kind of searching around on the net? And one approach to show that this is actually sufficient is to consider the process in 3 stages. There's a software construction stage, which we don't know much about, where the standards are very elaborate on what they expect. But there are also 2 further stages that are very important. Number 1, we can see that there's very many redesign discussions and bug fixing happening, even after the software was constructed, or while the software is constructed in an evolutionary process. And we find various bugs after the release. So there's some kind of post-priori bug discovery. So now we can consider, is this bug discovery good enough? What kind of bugs does this bug discovery detect? And if so, what can we learn about the software construction process from this bug discovery? So the steps really are, we're going to look at the bug discovery, see what kind of quality do we have? Do we find them in various interesting subsystems, or is there only bug discovery in one part but not in another? What kind of bugs are found? Are those obvious and critical bugs, or are there corner cases? What is the amount of bugs in the different bug classes that can tell you something about potential weaknesses in the software construction process? And what is their impact on your safety-related requirements? Are they somehow functional bugs or very specific APIs, or are they bugs that actually can harm your very top-level safety requirements? If you take all that into account, you have some kind of good feeling on, okay, what kind of bugs do I need to expect? I'm going to then show, well, there's actually a stability in this bug discovery and the impact. So there are no surprises that even if something was released at 10 years down the road, some very critical bug was discovered, or if it was discovered, then it's because of some kind of changed system context that was never even assumed to be valid in the first case. And if you have all that, you have quite some data that you can compare to an internal company reference. And you could then consider, okay, if the risk of using this internally developed component with, let's say, a similar number of and similar type of bugs is accepted by your company, then also it should be acceptable to use the Linux kernel in a specific context with specific requirements as well, just from a company risk perspective. Okay, so a second approach to show sufficiency is to show that the requirements you have are consistently being met. Again, remember we have tests, and for those tests, we could show that they are testing specific requirements that we care about. Also, the Linux kernel comes with millions of different versions. So we could check version by version if a test is actually succeeding or failing. And if it is consistently met, then obviously this must happen by some kind of stable process, right? If it wouldn't be intended to be met, then you would see outliers or a long phase of some require not being met, and then after years being met again, and so on. And so you would observe this kind of non-existent feedback cycle or existing feedback cycle. Of course, there's kind of a catch to it. If your tests actually aren't effective to detect the requirement, then you're screwed. So basically, we have to show that the tests are effective. Again, you can inject a fault, or you can break the requirement on intent by fault injection, and then show, okay, yes, my test will actually fail. So it will be effectively detecting if something goes wrong. And a second shortcoming is that you need to show that you're really testing different software stages of that software evolution. So actually the changes made could have potentially made that test fail, but the change that was then selected was the one that didn't break that requirement. Again, you can make some kind of static impact evaluation of the change. What kind of characteristics do the changes have? And you could generate, say, similar changes by kind of modifying the code as fault injection and showing, well, alternative change of very similar type of that change, what I have seen, would have actually been this thing, and this thing would have made the test fail, but it never actually was proposed, or if it was proposed, it was rejected during the development. And with that, you have your argument that some requirement is actually being met consistently during development. And with that, you can say, for sure, it has happened in the past, and it's likely to happen in the future as well, as long as the organization and the setup and the capabilities of that development doesn't significantly change. Okay, so we're going to come to the quick summary. I've shown you 5 approaches. You can mitigate the propagation of faults by some kind of detection and control. You can apply a diversity. You can use proven in use. You can try to argue the product quality by generating work products and evidence, or you can argue the process quality by showing that things that you extract from the development process show a certain stability with respect to the requirements you're interested in or the bugs observed. Okay, so let's quickly conclude. You can see there are many approaches possible. And in fact, in the past, many projects have been successful by selecting and combining elements of these basic approaches. So often the question on the ELISA mailing list is, oh, when are you done yet? And I think I can honestly say I've been now active in various safety argumentations, and the answer in every time was, we're done last year. You're always done last year, but it's a certain assumption that you have made, a certain selection and combination of approaches that has led to that success, right? And actually the success is determined by a number of factors. Number one, can you actually align with the system architecture that you have at hand? Or is it kind of assumed to be unmodifiable? What is actually the capability and expertise in your team working on the safety argumentation? Then a certain approach might be possible and others are not. What are the acceptance criteria of the chosen assessor? Some assessors might follow your argumentation. Others say, okay, this brings too much risks as it's a novel approach. And what is actually the criteria of the company you're working with? Because that is the one that is going to carry the business and liability risk in the end. So if you take that into account, you can go through the necessary interpretation, judgment, and mapping of the different techniques and measures behind those approaches, and then actually reach a suitable safety argumentation for your system where you're using Linux in a safety application. Okay, and with that, I'll open the stage for questions.
So Lucas, there is a question if we can share or you can share the slides with the webinar
Sure.
participants.
Yes.
So
I'll certainly can share the slides. And I think Min and I will take care of that. I think after this presentation, that will get them in the appropriate place.
Yep, so we'll definitely be sharing the recording, and sounds like it's okay. We have Lucas's permission to also share the slides as well. So that question's answered, and there are a couple of technical questions on the chat and also in the Q&A window.
There's a Q&A window as well. Ah, I see. That's crazy. Okay, too many windows. Okay, I'll start with the question from Allison. and I'll read it out quickly. So Allison proposed that you can create a safety case where you have a diversity of having some safety process running on an RTOS, right? Like Zephyr or Safe RTOS or various others. And you have a main processor running Linux. And the question is there a published safety analysis for this case? To my knowledge, I have not seen a published safety analysis for that. I think what is closest to a safety analysis of that is some work on that was done by Drive-by-Wire that considered that, but I'm not aware of anything published beyond that. I think as well you're going to look into what is the application, what is the possibility that your monitor that you're considering on the RTOS cannot catch the fault of the, let's say, computing on the Linux system. But again, that's, yeah, you have to look in that application specific probably. Okay. Then I'm gonna take the question from Luigi. And Luigi is asking, what's the opinion about the role of the man pages as source of specification? Yeah, I think often what we see is that when we make these safety arguments, we abstractly refer to the POSIX standard, because that's, of course, kind of one of the first sentences with which Linux was developed, and you can still see that pointer in the documentation. It says Linux is intending to implement POSIX. Interestingly, while that statement was certainly true in 1990, we now have 35 years of, or 33 years of work on Linux, and I think that actual implementation and the core functionality is far beyond that what is defined in the POSIX specification. So the man pages start to become much more relevant as specification, even if the specification is kind of created after the implementation and kind of also in retrofitting effort, but at least they are involved in the discussion. They take the specification, or they take the implementation and document how it works. And we can see that there's some kind of feedback loop as well. So I think you'll see that once, for example, for C groups, there's a C group version 1 and C group version 2. And obviously, by kind of starting to document how the API works for C groups version 1, people realized, okay, this is really not the best way to kind of describe the behavior we want. And that's why there's C groups version 2. It's different implementation and a different specification. So this kind of feedback loops exist. Okay, and I'll jump to Randy's question. Yeah, so again, that's the question is, a number of companies offer pre-certification of either proprietary OS or other components. Well, we know the competitors. do you think portions of Linux could ever be pre-certified out of context? And the answer is the wording out of context. So of course, when it's a pre-existing element, something always happened out of context because it pre-existed before you built your system. So there is an assumption of the developer making a context in which this software would be eventually deployed into. In that case, it is out of context, and that's the assumption. And then what you're doing is you're building a system and you're building up a context, and then thinking that Linux is the right choice for that context. I cannot answer to you if those two contexts are close enough to each other that you would say it's acceptable. If you do not understand how Linux was intended to be used, and you build a system that relies on each and every possible property of the Linux kernel, no matter how coincidental or unintended it actually is, then of course you are going to be in trouble. But that doesn't mean that all systems are that Linux doesn't fit to any systems at all. So again, right, this out of context is a very dangerous wording. It exists already by definition when you're looking at pre-existing software, but you need to understand what that actually means for you. And I think Chris already pointed that out. So out of context is this terrible wording to be used for pre-existing software anyway. And I think there's only one question left. There's a question again from Allison. Should we consider the C library as part of the Linux certification? And of course, which kind of choices would be possible for a C library? So what I've talked about is, of course, approaches that you apply to the Linux kernel. You can also apply the same approaches and techniques to your C library. The Linux kernel is interesting again because of let's say the larger complexity and larger interactions that you see. C library is similar, but it has a few properties that might make your argument a bit easier in one or the other approaches. But basically, you can follow the same techniques. You can apply diversity by using different implementations. You can make arguments about the development process. You can make arguments around creating tests and showing some kind of work products after the fact. And of course, you could mitigate certain faults that the glibc or that generally the C libraries might have by detecting them on the application side. Okay. Any final question? And there is a final question. So I'll read it out quickly again. Are there any efforts in the community or in the ELISA working group to make test cases, tools, documentation available upstream based on the lessons learned by the members and companies in the working group? Again, I can't talk for the overall community nor for the companies, but generally, I think the activities that you can see I think those from Red Hat on mapping test cases to specification will also or could potentially motivate someone to add further test cases. But again, it's a community project. So if tomorrow someone comes around and says, here are 2,000 new test cases, please help me review them and add them to the upstream test cases that exist, that's our next mission. It's really up to the contributors in the future. Okay, and with that, I hand over to Min again.
Great. Thank you, everybody, for attending the seminar talk. We will get the recording and the slides distributed in the next few days. And yeah, and we welcome everybody to participate in the ELISA project, all the working groups. Just go to elisa.tech. You'll find all the details about the project and how to, all the various channels that you can contribute. So thanks again, and we'll see you and talk to you online soon. Bye.
See you. Bye.